Imagine a universe far more intricate than anything we can see or touch. What if the world around us is just the surface of a deeper, hidden reality? What if our familiar experiences of space and time are just the tip of the iceberg? Today, we're diving into string theory, a groundbreaking framework in physics that might unlock secrets about the universe. This theory not only aims to explain the very fabric of reality, but also introduces the tantalizing idea of dimensions beyond the four we experience. Have you ever wondered what it means to go beyond the three dimensions of space and the single dimension of time? Could these hidden dimensions hold the key to understanding everything from black holes to the Big Bang? In this video, we'll uncover the mysteries of string theory and explore the possibility of dimensions beyond the fourth. Prepare to embark on a journey into the very foundation of existence. At its core, string theory is a bold and elegant attempt to explain the universe in its entirety. Instead of viewing the universe as composed of point-like particles, string theory suggests that the fundamental building blocks of nature are incredibly small, one-dimensional strings of energy. These strings vibrate at different frequencies, much like the strings on a musical instrument, and each specific vibration gives rise to a different particle. For example, one vibration might produce an electron, while another might create a quark. What makes this idea so revolutionary is its potential to unify all of physics. Traditionally, we have separate theories to explain gravity, general relativity, and the other fundamental forces, quantum mechanics. String theory, however, provides a single framework that can describe all forces and particles, earning it the nickname theory of everything. The origins of string theory date back to the 1960s, when physicists were trying to understand the strong nuclear force, the force that holds protons and neutrons together in an atomic nucleus. Initially, it seemed like string theory might solve this problem, but it soon evolved into something far grander. By the 1980s, researchers realized it had the potential to unify quantum mechanics and general relativity, two pillars of modern physics that had long resisted reconciliation. This evolution didn't happen overnight. String theory went through periods of intense development and criticism. The so-called first string revolution in the mid-1980s and the second string revolution in the mid-1990s introduced new mathematical tools and concepts that expanded its scope and solidified its role as a major area of theoretical physics. String theory's importance lies in its ability to address some of the most perplexing problems in physics. For instance, it provides a theoretical framework to reconcile the inconsistencies between gravity and quantum mechanics. Without such reconciliation, our understanding of black holes, the Big Bang, and the fundamental workings of the universe remains incomplete. Beyond unifying forces, string theory offers intriguing insights into the very nature of space and time. It suggests that space-time itself might emerge from the vibrations of strings, fundamentally altering how we think about reality. Moreover, it raises profound questions about the structure of the universe, including the existence of multiple universes and the role of higher dimensions. Let's start with the basics. Dimensions are the measurable extents of reality in which objects exist and interact. We're all familiar with the three spatial dimensions, length, width, and height, which define the physical space we live in. The fourth dimension, time, adds a dynamic element, allowing us to describe motion and change. Together, these four dimensions form what physicists call space-time, the stage on which all events in the universe occur. But what if there's more to reality than these four dimensions? Could there be additional dimensions that we can't directly perceive? One of string theory's most fascinating claims is the existence of additional dimensions beyond the familiar four. To work mathematically, the theory requires at least 10 dimensions, 9 spatial dimensions and 1 time dimension. An advanced version of string theory, known as M theory, even posits the existence of an 11th dimension. These extra dimensions are not part of our everyday experience because they are thought to be compactified, meaning they are curled up into incredibly tiny shapes. Imagine rolling up a piece of paper into a tight tube. From a distance, the paper might look like a one-dimensional line, but up close you'd see its true two-dimensional structure. Similarly, the extra dimensions in string theory are hidden at subatomic scales, making them undetectable with current technology. Visualizing higher dimensions can be daunting, but analogies help. Consider Flatland, a fictional two-dimensional world inhabited by flat beings. A 3D object passing through their world would appear as a series of strange shapes that the Flatlanders could not fully understand. In the same way, our 3D perspective might limit our ability to grasp higher dimensions. String theory often describes these higher dimensions using intricate mathematical structures known as Calabi-Yau manifolds. These multidimensional shapes are so complex that they can exist at every point in space, giving the universe its hidden depth. These higher dimensions are not just abstract concepts, they are vital to the functioning of string theory. For example, the existence of extra dimensions helps explain why gravity is so much weaker than the other fundamental forces. According to some models, gravity leaks into higher dimensions, diluting its effects in our observable 4D spacetime. Understanding these dimensions also opens up new possibilities for explaining dark matter, black holes, and the early universe. By studying these hidden dimensions, physicists hope to uncover clues about the nature of existence itself. While string theory is captivating, it faces a significant challenge: experimental verification. The strings proposed by the theory are so unimaginably small, about 10 to the negative 35th power meters, that no current technology can directly observe them. Testing the theory's predictions would require particle accelerators far more powerful than anything we can currently build. Similarly, the extra dimensions are so tightly compactified that their effects are incredibly subtle. Detecting these dimensions might involve indirect methods, such as observing anomalies in gravitational waves or particle interactions, but such experiments are still in their infancy. Some physicists criticize string theory for its lack of testable predictions. Unlike theories like general relativity, which have been confirmed through experiments, string theory remains largely theoretical. Critics argue that its reliance on complex mathematics makes it difficult to connect with observable phenomena, leading some to question whether it qualifies as a scientific theory at all. Despite these criticisms, string theory continues to inspire researchers. Its mathematical beauty and potential to unify physics make it a compelling area of study, even if experimental confirmation remains elusive. What if higher dimensions are more than just theoretical constructs? Some scientists speculate that these dimensions could harbor alternate realities, parallel universes, or shortcuts through spacetime such as wormholes. These ideas, while speculative, capture the imagination and hint at possibilities far beyond our current understanding. For example, some models suggest that higher dimensions could explain the nature of dark energy, the mysterious force driving the accelerated expansion of the universe. Others propose that these dimensions might contain entirely new forms of matter and energy, fundamentally altering our view of reality. If we could harness the properties of higher dimensions, the implications would be staggering. It might enable faster-than-light travel, opening the door to interstellar exploration. Similarly, understanding higher dimensions could revolutionize technology, leading to advances we can barely imagine today. While these ideas remain speculative, they highlight the transformative potential of exploring higher dimensions. String theory and its exploration of higher dimensions represent one of the boldest ventures in modern science. While the theory remains unproven, its ability to unify the forces of nature and reveal hidden layers of reality makes it a fascinating topic of study. By challenging us, to think beyond the familiar, string theory opens up new possibilities for understanding the universe and our place within it. As we continue to explore these concepts, one question remains. What secrets do these hidden dimensions hold, and how might they reshape our understanding of existence? If you enjoyed this journey into the mysteries of string theory and higher dimensions, don't forget to like, share, and subscribe for more fascinating explorations of science and the universe. And let us know in the comments, what do you think lies beyond the fourth dimension?